Okay, welcome back and we'll continue this. So we have found out this value, that is the resultant bending moment. We are getting at this point A as 756 Newton meter, and at the point B we are getting it as 819.2 Newton meter. So that also I can draw this using a straight line. I can join this point and here, and this is joined to the point D. These are all straight line. So when you draw, make sure that all this are straight line. And I can hash this portion. So referring this figure, we can see that the bending moment is maximum at the point B, that is 819.2 Newton meter. So we are having all this value required for calculating the diameter of the shaft. We have the stock value, that is 357.42 Newton meter, and we have the maximum bending moment acting at this point B, that is the resultant bending moment 819.2 Newton meter. Now we can do the remaining calculation. So we have this equation. According to this maximum normal stress theory, we have this equation A, and the maximum normal shear stress theory, we have this equation B. This is taken from the data book, page number 51, 3.6A and B. And we have found out this bending moment maximum value, and the torque also we are having. Now the unknown, that is a CM, it is a combined shock and fatigue loading for bending, and the CT, it is a combined shock and fatigue loading for torque, and the value normal stress sigma and the shear stress. This can be found out from this data book. So for that, let us take this. So here from this table 3.1, I can take that is a rotating shaft, the steady or gradually applied load condition. We have this value for CM as 1.5 and CT as 1. So that value I am writing it here. That is CM is equal to 1.5 and CT is equal to 1. That is from the table 3.1, page number 56. Now we will find out this value for the normal stress and the shear stress. So from this table 3.5b, we can take it as commercial steel shafting without allowance for keyways. Simple bending, that is the normal stress is equal to 110 Newton per millimeter square. And for torsion, the shear stress value, we can take it as 55 Newton per millimeter square. So that also I can take it and I can write it down here. Now we have all these values. Now the remaining step is we have to substitute this value in this equation A and in the equation B. So when I substitute this value, I can find out this diameter. So according to this maximum normal stress theory, this equation diameter becomes 16 by pi into sigma max. So sigma value we got it as 110 Newton per millimeter square. So the unit it is in millimeter. Now the remaining values we are to write. The value of CM it is 1.5 and M we are getting it as 819.2. Convert it into Newton millimeter, so it will be into 10 raised to 3. The whole thing raised to 2 plus 1 into 357.6 into 10 raised to 3. The whole thing square, it is the whole thing it is raised to 1 by 3. So when you do this, we can find out this diameter, and we are getting this diameter and this value we are getting it as 49 49.1. So this is 49.1. Remember this equation, we are taking it as equation number B, that is the normal shear stress theory, because it is written as 16 by pi into 110. We are having only the square root term. So this equation, it is actually the maximum shear stress theory. So we are having this equation B here, equation B. So the diameter we can calculate, and we will be getting this diameter as 49.11 millimeters. And the next equation, that is the equation number A, that is the maximum normal stress theory. There also we can substitute these values, and there it is 16 by pi into 110 into cm. Cm is equal to 1.5 into m, it is equal to 819.2 into 10 raised to 3 plus the square root value, it is equal to cm, that is 1.5 into 8192.2 into 10 raised to 3 the whole raised to 2 plus 1 into 357.6 into 10 raised to 3 the whole square, the whole thing raised to 1 by 3. This is the equation A. We are substituting these values in the equation A, that is a normal stress theory. And when we calculate this value, we are getting this value, diameter, it is equal to 48.79 millimeters. So when we use this maximum shear stress theory, we are getting this diameter of the shaft as 49.11 millimeter. When we use this normal stress theory, we are getting this diameter of the shaft as 48.79 millimeters. So always the greater value we have to choose. So we are choosing it as diameter of the shaft is equal to 49.11 millimeter. Now if we have a shaft with this dimension, the given condition will be satisfied. That means it can transmit this torque of this given value, that is 357.6, and also it can withstand this bending moment, that is 819.2 into 10 raised to 3. But we cannot manufacture this, we cannot fabricate this shaft, it will be costlier. So we have to purchase it from the shop. So in this dimension 49.11, it will not be available in the shop. So standard diameters will be available. So first we have to standardize this diameter of the shaft. So for that we can take this table, that is table 3.5a, standard shaft diameter, size in millimeters. We have to see which is a closer value, that is 49.11. So after that we have 49.11, we have 50. So we have to give some allowance. If we select this 50 millimeter, it is approximately 49.11. So we can choose this value 50, or we can go with the next value. That will be safer. Sometimes the load may increase. In that case also it will withstand this conditions, all the stresses. So it is better to choose this value 56, or we can go with this 50 also, but the safer side is we can choose this value 56 millimeters. So I'll write this, D is equal to 56 millimeter. So here it is. I am standardizing this value, that is diameter is equal to 56 millimeter. That is the diameter of the shaft. So if we have a shaft with this diameter, this given condition, it can transmit this torque on these two pulleys, and also this bending stress that also it can withstand. So we have seen this design of a shaft which is subjected to two type of loading condition, and the diameter of the shaft is equal to 56 millimeter. Thank you for watching. Thank you.